Right, year 12, just a little bit of feedback on this LED practical where we found the Planck constant. We plotted threshold voltage against 1 over wavelength. And this is what we got. Right, just first thing, need to get this off my chest. Quite a few of you appear to have started with the true value of Planck constant, which is 6.63 times 10 to the minus 34 joule seconds, and worked backwards, i.e., you've taken the true value of h, you've calculated what gradient that should give you on this graph, and then you've keyed in that gradient as your value of m. Now, I've no idea where you got that idea from. Okay, that is absolutely not what we do in experimental physics. If that's what we do when we do an experiment, physicists would find it impossible to make new discoveries. That's just not what we do. We go forwards, we take our measurements, and we plot the most correct and true line of best fit we can with the data we have. And then we use that to find out what our experiment says Planck constant is. Okay, so I was quite confused as to, it was quite a number of you, it was about half of you, seemed to think that working backwards was the right thing to do. So, and you miraculously got Planck constant to be 6.63 times 10 to the minus 34 joule seconds. I'm good, but I'm not that good because don't forget it was me doing the practical. Okay, right. This is what you got. Right, another thing. Can you, if you do a Desmos graph, please, can you share the graph with me? A lot of you giving me screenshots, which is nice. Okay, but I'm really keen to see the accuracy of your line of best fit. Now, this graph, I've just literally keyed the data in. This graph is not ready. We cannot do a line of best fit yet. All right, why? Any ideas? Okay, well, the points are all bunched up, aren't they? Yeah, they're all bunched up on the y-axis. So if we could try to do a line of best fit, but it's not going to be very accurate. Okay, so what do? We change the scales. So we go to settings up here, don't we? Yeah. Right, what we're going, so we're going from 0 to 2 on the y-axis, 0 to 3, 0 to 3, and 0 to 24 on the x. So here we go. Y-axis, 0 to 3. X-axis, 0 to 24. Now that should spread them out. There we go. Okay. Now that's when we do the line of best fit now, it's going to be much easier to get an accurate one. Okay. So as long as the points cover as much of the graph paper, as much of the graph area as possible in both the X and Y directions. That's important. Whenever you plot a graph by hand, that's what you do. You set out your axes so that the points cover as much of the graph paper as possible. Right, how do we do a line of best fit? It is this one, isn't it? Y equals mx plus c. Y equals mx plus c. Right, where's that line? Okay. I've just zoomed out because it's going to be much easier to do this part. So we want a positive gradient for starters. We want, now can you see here the sensitivity on the M is not ideal. So I'm going to have to key it in by hand, aren't I? So 2. That looks 1. So it's between 0.1 and 0.2. Okay. Right, now let's change the C value to get the line close. So the slider's okay, but the slider is definitely limited. All right. Now this is where we can zoom in, can't we? We can zoom right in now. So what do we need to do? We need to take it the closer to the origin. So let's take that down to 1510. Right, let's stick with that. Then we need to drop the gradient, don't we? So it's literally a case of just tweaking these values until you've got something that resembles a line of best fit that goes through the middle of the points. So we want to drop that gradient, don't we? We're getting closer, aren't we? And then let's take this value down. Almost there. We can drop that gradient just a little bit. What are we thinking? It's got to be close, isn't it? Boom. Right. So it just, I could not have done that. I could not have done that with my points all bunched up on the y-axis. Now that just literally took me 3 minutes, didn't it? Just tweaking the values of M and C to get as accurate a line of best fit as possible. So there's our gradient, 0.134. Now don't forget that that is not the gradient of our graph, because remember these values here, okay, the x values, this is 15.2 times 10 to the 5 meters to the minus 1, isn't it? So all these values must have a 10 to the power of 5 as well. So because this is on the x-axis, we're dividing by these values. The true gradient is 0.134 times 10 to the 5. Okay, and then we're going to use that to find Planck constant. All right. Okay, so that's what you need to be doing when you are plotting a graph in Desmos. Please share your graph with me, like I just said. I'd love you to see how accurate your line of best fit is. And then with the analysis, I've said this in a previous video, and I'll say it again, please. It's much easier for me and you for the analysis if you write it out on a piece of paper and just literally photograph it, attach the JPEG. Okay, if we're using powers of 10 and functions and equations, it's much easier than typing it out. Okay, and one final thing, please. I reckon about half of you did not include the unit for the Planck constant that you calculated. Now that is a shame, a real shame, to have done all this work to have quoted a value of Planck constant and not given a unit. All right, please can we tighten up on that. Anyway, apart from that, it's all good. See you later. Bye.